This is our last lecture on vector differentiation. Now, it'll turn up again when we're talking about path integrals, but this is kind of the last point of it. So, once again, we've talked about our path, where we just differentiate with respect to time. Our scalar field, where we can get a gradient. So, y initially is a shape, gets vectors. And then our vector field, which tells us about the flow and rotation. So, another way of doing divergence and curl is just the Jacobian matrix. And all the Jacobian matrix is a way of writing, differentiate everything any way possible. That's pretty much what it does. So, in 2 dimensions, you have some function f, which is function x and y, which is function x and y, and you just differentiate. The top row is fx with respect to both x and y. The next row is fy with respect to both x and y. In 3 dimensions, you have some vector field, which is a function of an x component, a y component, and a z component. And to get to Jacobian, you just take the top line, which is for all of fx, and differentiate that with respect to x, y, and then z. So you get three things. Here you get 9 answers. Yeah. Next line, you do it for fy, differentiate with respect to x, y, and then z. And lastly, the z component and differentiate with respect to x, y, and then z. So you have 9 derivatives. Yeah, 9 in total. You start with 3 and you end up with 9. You can have a non-symmetric version where you're mapping from 3 dimensions to 4, and Jacobian has to account for all these differences. Yeah. Or you can go from 3 to 2. There are reasons for these, but we don't use them. Now, what about the Jacobian in action? What do you do? So you have some function, once again, x direction, y direction, z direction, and you differentiate each of these. The diagonal of that matrix, so if you just add together a diagonal, it gives you your divergence. So if you have your 9 derivative, you just take the diagonal ones, add them together, you get your divergence straight off. And to get the curl, the things that aren't there on off the side, so you link that one with that one, that one with that one, and that one with that one, and you subtract them from each other, and that gives us our curl. So these 9 derivatives are all used in divergence and curl. And so if you have the Jacobian, you don't have to calculate the curl again, you don't have to calculate the divergence again, you can just take these values and put them in. Yeah, should all fall into place. Note though, always remember that there's a -1 here, and so it's this minus that, this minus that, this minus that. Yeah. And if you set up your matrix correctly, it's all very straightforward. Just so you know, there's something further than this. So if we have displacement, velocity, and acceleration, what we have is a vector field, Jacobian, and the Hessian. So this second derivative of the vector field, we don't touch on it. That's Christopher Walken playing the eponymous Hessian. So, in summation, we've looked at different cases where you have one variable or many variables, and we have our path integral, path derivative, our scalar field, and our vector field. And everything except for the path, you need to use the gradient. Yeah, and the gradient is a vector that represents the derivative, the x, y, and z direction as a vector. To take divergence, you multiply that by, or you do the dot product of that by your vector field. And to get the curl or the rotation, you do the cross product, linking together our earlier work with the derivative work. That sums pretty much that whole section. What you need to always remember is the path is very easy. You just differentiate with respect to t. Yeah. With scalar field, you use your gradient, and from the gradient is then used on your vector field to get divergence and curl. And Jacobian is just the same thing. It's just a slightly different approach of the same thing. So hopefully that's kind of cleared up a lot of the things to do with vector derivatives.